everyone. Thanks for coming to this talk. And today I'll be talking about where the field of foundation models are going, especially in this age of GPTs and chat GPTs and other kinds of large language models. I'm Som, I'm the director of AI Lab, and I run AI research within the Intel Labs organization. This is my team, so everything that I'll be talking about is really the hard work of all these wonderful researchers that work on these problems day in and day out. And as you can tell, one of the things we do is look at AI techniques, but also look at them from the point of view of scale, both from memory and compute perspectives. So the core point of my talk would be sort of asking three questions. We sort of start this talk with the general understanding that there's a perception that large language models seem to solve everything, and this is borne out by the rapid adoption of technologies like ChatGPT, as you can see in the graph on the left. Some things like Spotify or Netflix that we are eminently familiar with took years, a decade, more than a decade in some cases, to reach 100 million users, whereas ChatGPT reached that milestone in about 2 months. And in order to keep up with that kind of demand, there's been a frenetic activity, I think, on the speed and pace of the development of these new models. And as you can see on the right side, from 2017 when deep learning really took off to 2024, there's been a massive increase in just the number of foundation models that have been released. But as you can also tell, these are straddling sort of the very upper end of the training compute or the flops that are required to actually run this model. So this is becoming a point where these are extremely popular, but they're also very expensive in terms of computation. So really the questions that we're asking is, what is next in this whole paradigm? So the three questions I'll try to answer in this presentation is going to the very foundational question. With LLMs being this popular, we revisit the question of, is language even the best representation for all types of knowledge? Are there inefficiencies in that kind of representation, which maybe is leading to very computationally expensive machine learning stacks that are built on top of it? Then we ask the question that once you think about complex reasoning and in logical reasoning and things like that, as humans, we know that context always helps. So what does context mean in terms of foundation models? How do we enable these machine learning models to reason over very long contexts, both in time and space? And once we do that, then what kind of cool applications would this enable that are disruptive in nature? And the last question we ask is, beyond thinking about consumer use cases like, for example, text modalities or video modalities or images and things like that, are there really tough problems in engineering and science where AI and foundation models in general can disrupt? So the first topic is language the best representation. We introduce this line of thinking through a new type of framework, which is knowledge graphs. But before I get there, I want to give like a very simple example, which exposes some of the weaknesses of LLM. So I went to ChatGPT. This was a few months ago, actually. This was not the latest and greatest version, and simply asked the question: a man, a goat, and a boat are on one side of a river. How can the man cross the river? And so ChatGPT gave me this very long-winded answer. And as you can tell, with GPT having been trained on very large-scale internet data, it has seen a lot of patterns of this variations of this question that relate to a classic puzzle. And so this is what it regurgitated, right? So, and it gave an answer that is complete nonsense. The real answer to this is the man just rows the boat across the river and he's done. So this is a very nice example that the kind of next token prediction that GPT or variations of LLMs are doing are a class of machine learning architectures that do approximate retrieval. They're essentially retrieving the most probable next token. Now, it might look like logical reasoning because these models have been trained on massive amounts of internet data. So even though they're spitting out the next possible token or the next possible word, that looks like reasoning because a lot of the internet data that they have been trained on are actually examples of actual reasoning done by humans. But there's really no mechanism to do explicit reasoning within these LLMs. And this is why it fails on these kind of logical reasoning tasks that twist the questions a little bit to sort of be out of distribution of the data that it was trained on. So to answer, sort of to tackle challenges like this, one of the things we looked at is, the basic data structure. Now you can, think of language as one way of representing knowledge in the world, but there are some other techniques. And one of the very interesting ways of representing data is these data structures called knowledge graphs. And knowledge graphs are, pretty self-explanatory, as you can see in this figure. They tend to sort of relate entities and relationships between entities. So as a typical graph is constructed out of nodes and connections or edges between the nodes. In the case of a knowledge graph, these nodes could represent, various kinds of entities. Like in this case, we're representing people and places of interest and things like that. And the edges between them are representing all kinds of relationships, like has this person visited this place, or is this person interested in, this Mona Lisa, for example. Now, in this graph, you could, in a very compact way, represent a lot of things. If you just stare at this graph, you can see that it's representing things that relate to, dynamics or relationships between various kinds of entities. Now, to represent this exact knowledge base in English words would be a lot more inefficient. Now, you can imagine that this could be, for example, a web retailer that has a knowledge graph that relates to sellers and buyers and objects that they're selling and things like that. And it would be a lot more efficient to represent that kind of internal data on a graph structure like this rather than actual English text. And one of the machine learning problems that you can solve on a data structure like this is to ask questions about relationships that do not explicitly exist in the graph. So for example, here, there is no explicit representation of whether Lily, this node, has actually visited the Louvre. And in a typical machine learning framework, in order to answer this question, we build a neural network stack on top of it. And because this is being built on top of a graph, we call it a graph neural network. And you can emit sort of a probabilistic answer in terms of what is the probability of Lily having visited the Louvre. And the way you would do it is essentially looking at all the other secondary hops. For example, Lily is a friend of James. James has visited the Louvre, or Lily is interested in Da Vinci, and Da Vinci painted Mona Lisa, which is in the Louvre. So there's all these secondary paths that a machine learning stack can take into account in order to produce a probabilistic answer of whether Lily has actually visited the Louvre. So this is exactly what we built. This is called a knowledge graph reasoning problem, and Intel Labs built Ultra, which is open source, and it is the first knowledge graph reasoning foundation model. We call it a foundation model because, as you can see, we really pre-trained this model on 3 open source data sets. And as of today, this is a slightly outdated graph, but as of today, Ultra outperforms the state of the art in about 70 open source data sets that it has never seen. And so this is why we call it the first knowledge graph reasoning foundation model. And some of the cool things you can do with Ultra is shown in this demonstration. So here, for example, this is a knowledge graph that relates to various kinds of scientists, where they were born or which academic institution they went to. And one thing you can do with Ultra is ask a very simple question. For example, you can ask which country of citizenship relates to Euler, right? So you can ask that question. And you can ask the same question to an LLM. So from that perspective, right now, this doesn't look like so groundbreaking, right? So with this kind of a query, Ultra would produce a series of answers that relate to what its predictions are about Euler's country of citizenship. And it is important to note that this information is not explicitly present in the graph. This is something that Ultra is inferring based on other secondary hops. But here's something that Ultra can do that LLMs can't. So for example, you can click on the answer that Euler was Russian and ask the question to Ultra, why do you think that Euler is Russian? And this is where Ultra can actually retrieve all these secondary paths that actually explicitly exist in the knowledge base, or in this case, the knowledge graph. For example, Euler spoke or wrote in Russian, and Russian is a language that's spoken in Russia, or was spoken by Lev Gumilyov. Lev Gumilyov was a citizen of Soviet Union, so that produces sort of a vote of confidence that maybe Euler was Russian. And then it produces a series of these kind of secondary paths that actually explicitly exist in the knowledge base. So this provides the user with a way to debug the system and really get deep into the understanding of why a certain output was provided by that foundation model. So this is not maybe entirely logical reasoning, but it's a lot closer towards logical reasoning than, for example, the example you saw with ChatGPT earlier on. And we extended Ultra to perform even more complex reasoning. For example, in the previous demo, we showed you an example of a single question, which would relate to predicting a single relationship between a pair of nodes. But we've already expanded Ultra to ask very complex questions, which require multi-hop reasoning over multiple nodes, right? For example, what universities, the Turing Award winners in the field of deep learning work. So Ultra has to do a lot more under the hood reasoning to figure out who are the people who actually work in the field of deep learning, and of those people, who are the ones that won the Turing Award, and of those people that won the Turing Award, which universities did they go to? And so the same kind of reasoning happens under the hood, and Ultra provides the user with the same kind of explanation mechanisms, unlike what you'd find in an LLM. So with that motivation, we can now see that I think this is one area that the future of foundation model is heading towards, which is explainability, and this is particularly critical for sort of enterprise applications which require debuggability or some mechanism to explain why an outcome was provided. But regardless of whether LLMs or knowledge graph reasoning is the future, one of the things that really make complex reasoning work is the ability to aggregate context. And when you're aggregating context, you're doing this over hopefully longer and longer periods of time. The more context you have, technically you should be able to reason better. So the next question we ask is, how do we enable long context? Because it's fundamentally a computation and memory problem, right? You can't have infinite context because you don't have infinite memory or compute. So, and this is obviously borne by, again, a similar view of the graph I presented earlier, which is, parameter sizes are exploding. Context length that are supported by the emerging foundation models are also exploding, partly to account for the fact that you need that kind of very long context to perform good on reasoning tasks. But the fundamental problem is with LLM-like architectures, as you're, for example, having a conversation with an LLM agent, every piece of conversation you have with that agent increases the amount of context over which you have to reason, right? And these are articulated in the context of transformer architectures by this idea of tokens. Every piece of conversation you have back and forth with ChatGPT, for example, generates more and more tokens. And every token that has been produced as part of that conversation has to be taken into account when GPT provides you the next answer. But given that this is essentially becoming an unbounded sort of tokenization problem, you're hit with a memory wall. In fact, one of the things that we looked at was compared to the memory consumed by the actual GPT models or actual foundation models or large language models, how does that compare with this growing memory of context? And it turns out that depending on how you're serving these models, for example, if you have a batch size of 100 and a sequence length of 1,000 tokens, or equivalently, if you had 100,000 tokens and you're just serving one instance of a model, the KV cache size, and the KV cache essentially articulates, sort of takes into account this ever-growing cache of context, that actually grows way more than the model size. And so model size, even though it seems like there are trillion parameter models that are coming out every day now, they are no longer the bottleneck. The real bottleneck is all the context that needs to be stored in memory in order to keep having a conversational sequence. So to solve this problem, the obvious answer would be, okay, just like we compress models, or just like we compress quantize models or quantize activations, maybe we can just quantize or compress this cache of context, right? And so that's the obvious thing that the academia had tried. And a lot of people went out and quantized these KV cache to 2-bit or 4-bit quantization levels. But obviously, the real problem with that is you're going to lose information because of quantization error. So what we developed in our lab is this technique called GEAR, which is a near lossless compression technique. It borrows a lot from classical communication theory and signal processing theory. And essentially, what it does is it provides a way to retain some of the quantization error that's produced as part of the quantization, and allows you to recover that error during the inference process. And what we've shown is that by doing so, you can significantly reduce the memory footprint. For example, you can here see when we try to do when we applied this to Llama 2 13 billion, if you did no compression on the cache, then it rides way above sort of the memory capacity of even A100 or Gaudi 2 or even H200, which are sort of the mainstream accelerators and GPUs today, right? But if you're able to apply gear, which gets you to these red bars, you go significantly lower on the memory footprint, and you're actually able to accommodate these even on what is considered consumer grade A100 GPUs today. And the best part is that this comes with very little loss in the actual performance, which is what we are showing in this graph. So as you can see, what we are showing here is that we are applying this to, I believe this is Llama to 7 billion. And if you simply quantize the KV cache to 2 bits, which is very aggressive, and you need to be that aggressive because the cache is so large. If you have no error recovery mechanism, then all of these different variations of quantization lead to a lot of loss in accuracy. And this is simply unacceptable, especially in this kind of loss is unacceptable in the case of enterprise applications. But with two different variations of gear that we developed, you're able to actually recover this performance back. In fact, you're able to basically come back to the same performance as the unquantized cache would have been. So this is really quite compelling because this means that you get the benefit of a 2-bit cache as opposed to a 16-bit cache, but you're not sacrificing anything in terms of loss of performance. And this is also borne out by this other graph, which is saying a similar thing, where we try a number of different off-the-shelf quantizers, and the same trend exists. Whether we are quantizing these things to 4-bit or 2-bit, gear is always able to get back the performance loss. And the other angle to think of also when we are thinking about scaling context is memory is one part which we tackled earlier, but there's also compute, because these models are very, very large, and the longer context you have to compute this metric called attention over an ever-growing size of context. And these computations are not cheap, right? So one of the things that we recently developed in collaboration actually with Google DeepMind and Georgia Tech is a transformer variation of a transformer that is completely multiplier free. And what we are doing here is we essentially remapping the multiplications to be powers of 2. And therefore, we can get rid of the multiplier libraries and simply do shift and add operations at the bit level. And that has significantly cut down on the amount of computation needed and makes these kind of very large foundation models possible to run on consumer-grade hardware. So all of what I said so far relates to how do we scale up existing LLMs and existing foundation models. But where is this field really going? And to answer that question, we have to take a step back slightly and think of this problem from first principles. So the reason LLMs have been so successful is because of this fundamental architecture called the transformer. And what the transformer does is it has a representation in the form of tokens of your entire context, and none of your tokens are really ever thrown away. Your tokens are always there, and whenever you're trying to sort of predict the next token, it performs this kind of a attention or cross attention mechanism that relates to a pairwise computation or a pairwise correlation between every token you have seen in the past. So as you can see, since the token cache itself is growing, computing this pairwise function becomes increasingly expensive. So people started to ask the question, is this really necessary to keep every token from the past, especially as we move on from text-centric foundation models, which is the classic language models, to multimodal foundation models, which are now taking into account audio and video and speech and so on and so forth. And the simple answer is no, because if you take even a simple signal like audio, these are extremely compressible in time. There's a lot of correlation between one sample of audio to the next, especially if they're right next to each other. So it really brings into question whether we even need sort of this high precision access to every token that has been generated in the past. And this thinking has led to completely new architectures that are not attention centric, that are not essentially not transformers at all, but they try to compress your entire past context into a fixed memory footprint, which is called a state. And that is what led to sort of this explosion of architectures called state space models, which you might be familiar with. Particularly Mamba is a very famous one. But in a very short period of time, this line of thinking has led to an explosion in a lot of other variations of architectures that also compress the past context. And as you can see from this graphic, there's probably like upwards of a dozen to 2 dozen architectures that what I would call mainstream today that are effectively competing with LLMs at the scale of double-digit billion parameters, but are significantly 5 to 10x faster or more memory efficient than LLMs are. So this is definitely a trend that I expect to be much more stronger, I think, in the coming months. So next we move on to the question of, okay, we've enabled long context when we can do a lot of complex reasoning over very long context, then but what are some cool applications that this can enable? And one of the application areas that our lab has been looking at is video understanding, and particularly on long form videos, because long context is the one that we are really interested in. And so to solve complex reasoning problems on videos, we started looking at this problem from, again, a graph-centric approach, because as I sort of mentioned in the first section, knowledge graphs are a very efficient way to represent knowledge. And we took that idea to videos as well. And we started thinking of videos as comprising of a bunch of frames, but within each frame, you have a lot of entities like people and animals and backgrounds, and there are relationships between entities. And if you can capture these entities and relationships as a graph over that frame, but then also connect these relationships across time, because video is a collection of frames in time, then maybe you're starting to look at a graph reasoning type of problem, and you can leverage a lot of work we've done in that area. And this is exactly what we did. We've sort of created this very sparse and highly efficient, video-centric spatiotemporal graphs that can support much longer context. For example, in these graphs, you're showing the length of the videos that these models can handle. And as you can see, these are significantly longer than the state-of-the-art transformer-centric models. But because graph neural networks are also sparse by nature, these are also significantly smaller in terms of their compute footprint. And we sort of took that idea to more emerging architectures that are transformer centric, and we built out what we think of as sparse transformers. And these kind of gains that we saw with sparse graphs also translated to these sparse transformers. And just to give you a sense of like what a sparse transformer is seeing, it's really seeing 10% maybe of the tokens that represent a video frame. So as a form of visualization, on the left side, this is an example of a frame of a person in a living room playing with a book, flipping through the pages. And if you want to do some kind of a video question answering with this kind of data, this is the type of data that would go into the standard transformer. But our sparse transformers is 90% sparse most of the time. And as a form of visualization, this non-blacked out pixels are actually what the transformer is seeing. But we're able to maintain the performance as if we never, sparsified these inputs. And similarly, we also started leveraging sort of the emerging open source foundation models that people have already been developing. And we figured that maybe, given that these foundation models like Lavila, for example, are already being trained at great expense on short form videos, is there a way to leverage these short form foundation models to do long form reasoning? And the very simple insight we had is maybe if we use the off the shelf short form foundation models to just be the token generator, and maybe we can train another hierarchical foundation model on top of it to actually do the long form reasoning. And that way we can keep the cost of training these long form models significantly smaller. And this is exactly what we did. And this paper was at CVPR this year, and it's called Leviti. And very simply, it allows us to handle videos that are 20 to 50x longer than what the standard Lavila or other standard video foundation models can handle. And so these are sort of, this graph is showing that exact thing. These are the sort of baselines. Typically, they would handle videos that are about 16 frames, because videos are obviously a lot more memory intensive than text. So it's rare to see these models handle videos that are more than 16 frames at a time, whereas our version, which is Leviti, can actually handle 1,000 frames at a time, which is essentially untrimmed videos, because of the fact that we have this hierarchical architecture. And that leads to, these kind of things really lead to some compelling, applications. For example, you can now use this to compress a very long video, right? So we call this like the highlights reel or video summarization. So if you're trying to summarize a very long video, we took a look at this open source data set. And what this is showing is the middle panel is a ground truth summary of what humans thought was a good compressed representation of a video. So this is already sort of the highlights reel for what was likely a much longer video of a plane landing. And as you can see, most humans thought that the actual landing part is the more interesting part, right? And on the left is Video Sage, which is our version. And as you can see, for the most part, it matches what humans thought were interesting. Whereas the previous state of the art, which is PGL-SUM, actually doesn't get that. It's producing summary videos that are actually a lot more boring. And you can see the same thing happening with the bottom frame, for example, where the Video Sage actually catches on to the interesting parts of the video much faster than the existing state of the art. And the reason why this is happening is because with Video Sage, because you have a much longer sort of context that is able to be represented, as it's generating the summary videos, it knows that it knows how interesting it is or not with respect to the rest of the video. Whereas a technique like PGL-SUM, which has a very small attention span, let's just say, it's generating these frames of summary frames, but it doesn't know that the summary frame it produced a few frames earlier is actually pretty much the same as the one it's producing now, because it just doesn't have that sort of attention length. And so this is what happens, in this case, on the bottom part, it continues to generate sort of what I consider boring parts of the video, or what humans would consider boring parts of the video, whereas Video Stage actually quite nicely matches what humans thought were interesting pieces of that video. And because we are able to do this, we can also, sort of get more accurate retrieval in terms of time. We can embed like temporal context in these models, and you can do things like where you can do sort of a running summary of what's happening in a video. And so this is really cool at kind of chatting with video kind of an application where almost in real time, while these videos are streaming, you can actually ask questions, or in this case, we are showing a case where it's a running sort of commentary on what's happening in the video. But you can imagine with this kind of ability, you can also do a live question answer with the video to ask what is happening in real time. So with that being said, this is my last section. We talked a lot about consumer applications. We talked about LLMs. We talked about increasing context, and we talked about consumer use cases like video. But one of the things that keeps us quite interested in this field is what can we do in the fields of hard engineering problems or hard scientific problems. And I'll end this talk with a couple of examples of things we are doing in the world of computational chemistry and chip design. So in the world of computational chemistry, one of the really cool problems is to think about molecules, right? So molecules, again, when we machine learning researchers look at a molecule, we see a graph, because we see a lot of atoms that are connected with some kind of an energy bond. The energy bonds look like edges in a graph, and the molecules or the atoms look like nodes in a graph. So a lot of the stuff I described earlier with knowledge graph reasoning or with video graph reasoning can really, at an abstract level, apply to discovering new types of molecules. And so this is exactly what we did with this really cool project, which is called ProtestT, where you could actually combine a large language model, like an English language model, with another, I want to say maybe language model, but protein language model, which is really treating proteins as a sequence of amino acids, and the sequence of anything can be thought of as a language in abstraction. And so a lot of the things that we built out in an LLM architecture, we applied to the protein sequences. And so you basically have two representations. One is an English language representation from your standard off-the-shelf LLM, and a protein language representation that comes from understanding sort of protein sequences. And the cool thing is now you can actually combine these two at the embedding layers to actually now do query answering on structures of proteins. Like you can, for example, ask the system to retrieve protein 3D structure that has certain properties, which is sort of highlighted in a couple of these examples. And you can do this in English language. And the backend can actually now relate the English language query to the embeddings of the structural embeddings of the 3D protein structures and retrieve candidate proteins that actually satisfy the properties that you're asking for. This is the kind of disruption that you can now start building if you expand your thinking about language models and what is language anyway to thinking more of sequential problems. And we're doing a lot of work in this area in general, sort of establishing new benchmarks. Earlier, I showed, the protein example, which maybe broadly relates to things like drug discovery. But at Intel, obviously, we're not developing drugs. We're developing semiconductor technology. And a core part of that semiconductor technology is semiconductors themselves. So a lot of work is happening in our team to develop new benchmarks and new tools for discovery of new semiconductor materials. I mean, at the back end, this is all really still molecular discovery. And in relation to disruptions in the semiconductor industry, we're also building co-pilot-like productivity tools for the material scientists who work at Intel, and obviously also in general in the semiconductor community. And what this demo is showing is sort of an agentic approach to making the lives of design engineers a little bit easier. So in this case, for example, we built an agent. We gave it a very simple sort of toy task to compute the energy of a hydrogen atom. In this case, the agent actually generates a code to simulate the behavior of a hydrogen atom and get the energy values, but it has a bunch of syntax errors. But being an agentic system, it's able to actually identify these errors, fix it, reruns the result, but still obtains invalid results because it doesn't have the right documentation in its backend to actually do some kind of retrieval augmented generation on or RAG on, right? But when we actually add that documentation, which is in this case called the AAC documentation to the database, the agent now is able to read on its code, which has now been fixed of all the syntax errors and things like that. And it's actually able to retrieve the correct information and deliver valid results. So this is the kind of disruption, again, that provides, it's hard to quantify how much it improves the lives of designers, but our feedback in general, working with business units at Intel, is that it is severely disruptive and in a good way. And in sort of, obviously we are a research lab, so we don't just solve problems for Intel. We also solve what we think of as foundational or frontier problems in the community in general. And as part of that, we've been able to attract a large range of collaborators from industrial research partners like DeepMind, as well as academic partners at MIT, to actually work with us to further these techniques in the community. One last example, we're also looking at other problems that are relevant to Intel. Previously, I talked about semiconductor material discovery, and this other project that we're looking at is accelerating physical design or chip design. And a key part of chip design is chip floor planning, which at a very high level is really a geometric Tetris problem. You're trying to fit as many oddly shaped or irregular shaped blocks with a large number of physical constraints and electrophysical constraints into the smallest area possible, while trying to respect the fact that you can't just overlap blocks on top of each other, right? So as simple as the framing of this problem might sound, this is a classic sort of, in some cases, NP complete problem, which is sort of a very open scientific problem as well. And so we've been building these models that take into account classical search techniques like genetic algorithms or A-star search or Dijkstra's algorithm that, for example, is used in shortest path planning. And of the many things that we built, one of the things that was really impactful recently is the fastest known floor planner or chip floor planner in the world, which takes about 15 minutes to go from a random assortment of partitions on an SoC or a system on chip to what would be considered human quality floor plans that are actually that respect all of the design constraints and electrophysical constraints that a typical human designer would actually take. And this typical process, it takes 15 minutes, whereas in a sort of a traditional flow, this would probably take hours to days, depending on the complexity of the chip. And in that same frame, we are building foundation model for all kinds of geometric and combinatorial problems that go below just the chip floor planning, even to the level of standard cell placement or macro placement. And the open research in this case is how can we really combine combinatorial search, which is a very classical non-machine learning topic, with new and modern approaches from machine learning that sort of comes from the age of LLMs and other foundation models. Hopefully, this gave you a good sense of what Intel Labs is doing in the world of foundation models as it exists today, what kind of applications and disruption it's bringing with the capabilities today. But more importantly, hopefully this gives you an idea of where the industry is headed, both in terms of model architecture, new types of training methodologies, or even new types of applications like computational chemistry or chip design. But going back to the original questions I asked, foundation models and LLMs still hallucinate, and there's an open question, open research problem of how do we make them not hallucinate, and how do we ground the performance of these models in actual knowledge. This debate is just getting started. I presented something on knowledge graphs, but there's a lot of open and emerging techniques that are trying to sort of address this issue. The second takeaway would be that we know the famous paper "Attention is All You Need," which started this whole era of transformers and therefore LLMs. But as I showed with my take on state space models and emerging architectures that are not transformers, it's turning out that maybe attention may not be all you need, especially if it's not language and if it's modalities like audio or video that are compressible in time. But regardless, the scaling of these technologies to very long context is crucial because context is important for complex reasoning. And it'll continue to be an open problem of how do we scale context, both from a computational and memory point of view, so that these foundation models are actually running on consumer grade hardware and don't require very expensive GPUs all of the time. And finally, hopefully, the last two examples of computational chemistry and chip design gives people motivation to think about foundation models or AI in general as a tool to solve some real hardcore science and engineering problems as sort of the next frontier. So that's it. Thank you, and hopefully you enjoyed this talk.